Mhm. Mhm.
Yet or not, it does. Perfect, that's perfect. So I'm just going to describe how this will go and then we're going to get started. Hey, I am going to share the screen now. So we're going to start with a group of presenters, and this will also determine the order in which we're going to go. So today is April 19, 2022, and this is the ePoster research sessions, and we might as well assume that we have started. So welcome everybody to our 13th research session, ePosters. This activity was started 2 years ago by John Candelaria from Stanford when he was the chair of this TAC. And it's now almost 2 years later, and we are on session number 13. 4 young researchers have agreed to come here to share their research with us. You can see their names on the screen, hopefully you can. Roshan Sajjad, Jemma Bennett, Kayla Rodriguez, and Joshua Leaney. We start now. This is recorded for your viewing pleasure, but also for quality control to make these productions better in the future. Each presentation will be about 12-13 minutes. There will be 2 or 3 minutes at the end for questions. And then at the end, depending on how things are, we might have a discussion, overall discussion. Christopher Bishop is present. I think that we need to promote the office hours on April 28. The Quantum Marketplace on the 5th of May is going to be on quantum computing. We'll have a lot of companies that are going to present. I believe Cold Quanta is coming, D-Wave, Quantinum, Q-Era, Xanadu, and more. And now this ePoster session. So I want to salute Charles Robinson, who is the current chair of this workforce development TAC, and Terrell France, the vice chair, who is, as far as I know, on an airplane at this time. So thanking the presenters for agreeing to come over here. I'm going to stop sharing the screen. I'm going to ask the first presenter to share his screen. While I introduce him, I'm going to say a few words about everybody as they start, and then I'm going to add something at the end. So Roshan is a 4th-year physics graduate student and NSF Quantum Foundry graduate fellow working with David Weld at UC Santa Barbara. Generally speaking, he says he's very interested in exploring novel phenomena using cold atoms, especially in the field of quantum simulation. As we normally do, I ask every presenter to describe briefly their research in terms that would be a high school senior would be able to relate to, for the sake of interest and inspiration. So he says, my research involves creating Bose-Einstein condensates, which is a phase of matter that is much colder and more dilute than typical phases learned in a high school chemistry course. Due to quantum mechanics, all atoms in such a condensate collectively act as a coherent wave, creating a fully quantum object and displaying behavior such as interference. Through interactions with lasers and magnetic fields, we use these condensates to simulate behavior in solid-state systems and explore fundamental physical phenomena, such as the quantum boomerang effect, which he will be talking about today. So I'm going to mute myself and I'm going to ask Roshan to get started.
Yeah, sure thing. Thank you for the introduction, and it's a pleasure to be here. And yeah, like Adrian said, my name is Roshan, and I'm a graduate student in the Weld Lab at UC Santa Barbara. And yeah, I'm pretty excited to share our recent work on observation of the quantum boomerang effect. And if you're interested after the talk, we recently published this in PRX a couple months ago, so you can check that out for some more info. Here's just a brief outline of my talk. I'll start by talking about 2 kind of theoretical concepts. One is the quantum boomerang effect itself, and the other is that of the quantum kicked rotor, which is the system that we actually use to see the quantum boomerang effect. Then I'll talk about a little bit about our ultra cold atom experiment and how we make BECs, and then finally end with how to actually destroy the boomerang. So just to start, what is the quantum boomerang effect? And just for some physical intuition, I'll have you just imagine a particle in an Anderson localized system. Anderson localization here meaning suppression of wave dispersion in the presence of random disorder. So you can imagine, let's say, an electron in an atomic lattice with defects, let's say. And so we're going to give this particle some kick, some non-zero initial velocity. And what you expect classically is that the particle will start at some spot at its origin, move away some distance, let's say some mean free path, and then localize somewhere else, which is kind of easily kind of calculated by this dashed line shown on the right here. What's interesting is that in the quantum case, if you have a wave packet, it'll depart from the origin, move some distance, and then kind of non-intuitively turn around and come back to the origin, kind of shown by this blue line on the right. And this is kind of neatly pointed out in this nice PRA article in 2019. And it's actually related deeply to this concept of time reversal invariance in physics, which I'll discuss a little more as I go through the talk. And what's kind of surprising is that Anderson localization as a phenomenon was predicted back in the 1950s, but this was only predicted 3 years ago, which is kind of a fundamental dynamical signature of Anderson localization. So it took like 60 years to actually find it, which we found kind of fascinating. Okay, but you can imagine that, in order to see this kind of effect, it's pretty difficult to track something like an electron atomic lattice. So we need to find some other system where we can actually see the effect. And the system that we're going to be exploring is that of the kicked rotor. This is kind of a paradigmatic system in nonlinear dynamics and chaos theory. And for some physical intuition, all it is a bead that's confined to a ring, that's periodically kicked along one axis. And it's described by this Hamiltonian. It's just two terms. It's a kinetic energy term and then a kick term with kick strength K and period T. So you're kicking once per period. And the reason this is such a heavily studied system is that depending on the kick strength, the dynamics can be chaotic. And so I show that kind of on the top right here with these two so-called Poincare maps. These are phase-space trajectories that are sampled once per period. So the x-axis is position and the y-axis is momentum. And what you can see is that for low kick strengths, almost all of your trajectories are periodic or quasi-periodic, kind of making these like nice loops or lines. But for larger kick strengths, basically all the trajectories are chaotic. And so they ergodically kind of explore the phase space that's available to them. And so classically, this system is globally diffusive, meaning that if you keep kicking the system and keep inputting energy, the energy of the system will continue to grow. But quantum mechanically, the behavior is fundamentally different in that it exhibits this phenomenon known as dynamical localization, which is equivalent to 1D Anderson localization in momentum space. And so just for some intuition, for those of you familiar with the Anderson model, it's a two-term Hamiltonian. You have a hopping term and then some random on-site potential term. And that's actually exactly what you have with this two-term Hamiltonian as well. So the kick term acts as a hopping in momentum space due to the fact that it couples different momentum sites together. And the kinetic energy term acts as a pseudo-random on-site potential because different momentum states wind different amounts of phase for the same amount of time. And so we're interested in the system for two reasons. One is that it's been studied in cold atom systems for the last 25 to 30 years, starting with these nice experiments in the 90s, which I show on the bottom right, where basically this data shows energy is a function of kick number for a kicked gas of sodium atoms. And what you can see is that after some amount of time, the energy saturates even as you keep kicking the system. So it's kind of a nice experimental signature of this dynamical localization behavior. And the other reason is that recently this system was predicted to show the quantum boomerang effect just last year, actually, in this nice PRA from Patricia Vignolo's group. And it's actually part of the reason why we actually decided to pursue this experiment at all. So how are we going to go about seeing this? Well, our lab makes Bose-Einstein condensates, so that's going to be our starting point. We start with about 100,000 atoms in our condensate, lithium-7. And what we do is we load them into an optical lattice, which is a retro-reflected laser beam of 1064 nanometer wavelength. And then we snap off the lattice and then quench into this Hamiltonian, which is the exact same Hamiltonian as the kicked rotor, but with this term alpha, which we'll call the Floquet gauge. And so physically, what it means to quench into this Hamiltonian means we snap off the lattice, we wait some amount of time, alpha times t, where alpha is a fraction between 0 and 1. And then we kick with a phase shifted lattice, similar to a normal kicked rotor protocol with some strength V naught. And so just kind of two things to note here. One is that this term alpha will actually set the time reversal properties of the system, which I'll actually talk about in 2 slides. And then the phase shift of the second lattice actually acts as our non-zero velocity. So when I talk about the normal boomerang effect, you have a non-zero velocity that brings you back to 0 average position. But in the kicked rotor, due to the fact that you have Anderson localization in momentum space now instead of position, so position and momentum are basically conjugate variables here, the phase shift in position actually acts as your non-zero velocity. And you can kind of imagine that occurring due to the fact that when you load into the initial optical lattice, you'll have your atoms sitting kind of in the troughs of the wells here. But then when you snap off and start kicking with the phase shifted lattice, they'll actually be localized on the slopes. And so that kind of gives you this non-zero velocity. And so after some number of kicks, we'll let the atoms freely expand in order to resolve their momentum states, and then we'll take images of them to actually do our data analysis. This is actually what the experiment looks like in real life. The top is a CAD model, and our atoms start kind of in this oven section on the left here. They come out pretty hot at about 1,000 degrees Kelvin. And then after a variety of laser cooling steps, they're trapped in the science chamber here, where we start with a magneto-optical trap. And then through further evaporative cooling steps, we end up with a condensate or boson-sand condensate at about 10 nanokelvin. So you have about an 11 order of magnitude jump in temperature to actually get to the condensate level. This bottom picture actually shows what the real experiment looks like. So the machine is in the back here with all of the BNC's fibers, electronics, and optics kind of in all their glory. And the front here is our laser table where we prepare all of our laser cooling light. And so for lithium, it's all at 671 nanometers. So our lab is very red. Okay, so here's kind of the main data of this experiment. So just for clarity, the x-axis here, again, is kick number, and the y-axis is average momentum. And what we see in basically every case, for every alpha, which again is the delay time, is that we start out at 0 average momentum, and then it'll depart and then saturate at some other different average momentum at late times. But for very specific values of alpha, namely those around alpha equals 0.5, what you see is the classic, or the kind of characteristic quantum boomerang effect, where you depart from 0 average momentum, go to some other value, and then come back and saturate to 0, even as you keep kicking the system. And the reason this happens is that if you look at the Floquet operator for this system, Floquet meaning kind of like the periodic time evolution. If you imagine what that looks like for the normal kicked rotor, you'll have some propagator for the kick and some propagator for the kinetic energy, and then you'll repeat those over and over again to construct the time evolution of the system. But for the boomerang, what happens is that due to this delay time alpha, you actually end up with 2 free propagators that sandwich this kick term. And exactly at alpha equals 0.5, these 2 free propagation terms become the same because alpha and 1 minus alpha end up having the same value. And so you can imagine that if you quench into this Floquet operator at the time t equals 0, running time forwards and backwards basically gives you the same thing, which is that you'll have half a period of free propagation, a kick, and then another period of free propagation. And that's really, we find that this is actually why the quantum boomerang effect exists at all. And so for all other values, you saturate to some, non-zero value. Okay, and then just kind of my last slide. We're experimentalists. So every time we find something, we like to destroy it and see kind of how it behaves. And so the last question we ask is, what happens to the boomerang effect when localization is destroyed? And so to do that, we can introduce some random deviation to our kick periods. Namely, the period t can go to some t plus delta n of t, where delta is drawn from some distribution, some random distribution. And so we'll characterize that with this variable capital delta, where if capital delta is equal to 0, there's no randomness at all. And if capital delta is equal to 1, let's say, then your just little delta of n is minus t over 2 to t over 2. And so this kind of introducing randomness is actually a way to go from the quantum to the classical regime due to the fact that this randomness actually breaks dynamical localization in theory. And you can kind of see that on the bottom left plot here. So again, this is kick number versus energy now. And so for the blue data in theory, what we see is typical kind of localization or dynamical localization for the no randomness case. But what we see is that when we introduce randomness, you get this kind of diffusive energy growth showing that the dynamical localization has been broken. And so now if you look at the boomerang signal, again, looking at average momentum versus kick number, what you see is that, for the no randomness case, you see this nice kind of blue boomerang here. But in the random case, what we see is a similar behavior for the first few kicks, but then actually some saturation. So there's no return ever. And we can characterize this basically by tuning delta. So on the bottom right here, we're looking at late time average momentum versus the degree of randomness. And what you can see is that basically you observe boomerang-like behavior when there's no randomness. And as you start to tune up the randomness, you depart further and further from the typical boomerang behavior. Okay, and so with that, I'll conclude. So we've experimentally observed the quantum boomerang effect and have investigated the effects of a whole bunch of different parameters, including alpha, the randomness and time reversal symmetry on the boomerang effect. And kind of the last thing I'll say is, why should you even care about the quantum boomerang effect, which I didn't really touch on yet. And there's kind of 2 reasons. One is that There's been some theory work done on exploring the system in the presence of interactions. So then it becomes a kind of a study of many body effects in an Anderson localized system, which is kind of the hot topic in condensed matter at the moment. And the other reason is that there's also been theory work done on exploring the boomerang in higher dimensions. And so in the kicked rotor, that really corresponds to adding multiple time axes. So you start kicking with different numbers of frequencies. And in, let's say like 3 dimensions, it actually is a good way to probe the regime between localized and delocalized states and studying things such as mobility edges. Yeah, great. And so with that, I'd like to thank my team, my PI, our funding agencies, and you for your attention. Thank you so much.
Thank you for this wonderful presentation, Roshan. And I want to say that at this stage, people should ask questions. If you have questions during the presentation, you can write them in the chat, or you can ask the questions now. Before questions come, I want to point out that we asked every presenter to provide their questions. And I have 2 questions that I'm going to address everybody that's from industry. So Roshan says, what skills do you industry members value most for potential applicants coming in with PhDs who have not necessarily worked in the exact field that your company is in? And there's a follow-up question, how common is it for people with PhDs to switch to something completely new when they enter an industry position? For example, is it common or even possible for people with atomic optical physics backgrounds to go into something like superconducting qubits or photonics? So this
is that question directed at us or?
Yes, the question is directed to everybody in industry, but I would single you out, Charles Robinson, who represents IBM Quantum. If he wants, he can answer, or anybody else from industry. Yeah.
Okay, so the answer is yes, these skills that you are learning and the deep physics understanding of theory and experimental research are absolutely critical for organizations like the one that I work in, IBM, even though everyone knows that we're looking at superconducting qubits. And the reason why is it is not a leap of understanding. It's all the same physics. And so in this case, I'm going to give a specific example. You use the lithium ion as the experimental object, which to me lets me know that in terms of that specific molecule, that you understand its properties, you understand how it is leveraged in this experiment, and so to do other experiments with the same material, it is not a, even if it's a different experimental apparatus. As an example, you're using cold atoms and lithium on an optical table. It doesn't necessarily mean that you can't do lithium experiments in battery technology using superconducting qubits. At the end of the day, it's the same experimental process. We use Hamiltonians too, right? It's all Hamiltonians. And at the end of the day, we look at all of the characteristics as far as what you looked at for analysis, right? The boomerang effect is real regardless of what experiments you do in physics. It's just one property that is, if you're looking at many body problems, it's going to be an issue. And you've come up with novel ideas on how to affect the environment, like, how to, in this example, you want to observe the boomerang effect, but then you went one step further. You wanted to destruct, by introducing randomness. And so all of these experimental ideas that you use, even though it's in a different medium, it's using cold atoms, it's on an optical table, it's using lasers, it's using fundamental physics, quantum physics. And so when we hire PhDs, we put them in all different types of areas at the TJ Watson Research Laboratory. Some of them are experimentalists, some of them are theory folks, Some of them are electrical and computer engineers. Some of them are chip developers. They all work together. Some of them are even customer-facing physicists and engineers that are experimentalists, right? To work with clients, experimentalists that are working on experiments in quantum. And so the answer is yes, they all apply. But the one thing I will say to any young student is that flexibility in your knowledge and understanding is something that I believe you should strive for. And you should be intellectually curious about all aspects of what you're doing there. And so I'll pause there. It was a long answer. Hopefully it made some sense. Roshan, I thought that this was very compelling, and I'll hold my questions until the question and answer section.
So I just want to jump in. I know we're running a little late. We want to make sure we get time for other presenters. I would say, just to echo what Charles is saying, certainly any kinds of meta skills around quantum and physics and quantum mechanics are applicable across a range of settings. That said, as you may or may not know, there's a whole ecosystem, right, of quantum solutions being developed. So for an easier transition, what I would say, for example, to you, Roshan, I would investigate companies that are using Bose-Einstein condensates. Quanta comes to mind, right? That'd be an easier transition for you. If you're studying superconducting, IBM is a perfect place to land. If you're into photonics, you're studying that kind of physics applications around quantum, reach for PsiQuantum or Xanadu, right? So just do a little research around what companies are using the kinds of quantum physics you're studying and reach for them. And they'd be delighted to hear from you, trust me.
Yeah, so I think we already asked him, and he already mentioned a number of companies where he might go. So for example, he mentioned QED, Atom Computing, Google, but the question was in general. If you finish with a PhD, then you are very specialized. Is it likely to ever be able or asked to switch trades, so to speak? And I guess that's what the two
No, I mean, from my perspective, right, you focus in a very narrow area of experimentalization, but that doesn't preclude you from understanding the broader context. And I think, it is a useful endeavor to focus, because then that'll allow you to focus on something else if you choose to, right? You know what I mean? And there's no, if you want to only be an experimentalist, and you want to solve a specific problem of interest in that specific area that you have interest in, then the best way to do that is to get funding and just do research in an academic setting, right? That's clear. You can do that. Folks spend careers doing that, and they change the world. Or you can be open-minded and look for other problems and solve problems everywhere. I mean, one of the things that if you look at some of the most famous mathematicians / physicists in the world, they studied a range of things. I'm just going to pause there.
Okay, so with this, I think we should go to the second speaker. Our second speaker is Jemma Bennett from Durham University in the UK. So it's 8:30 over there. So while she's hooking up the slides, I'm going to say that she's a third-year computational physics PhD student at Durham University in the UK, supervised by Professor Viv Kendon and Dr. Nicholas Chancellor. She is currently researching error suppression in continuous time quantum computing, and her title of her presentation is Error Suppression in Continuous Time Quantum Computing. Go, Jemma.
Jenny, you're on mute.
Why you unmute yourself first?
Sorry, thank you. Sorry,
No
thank you
problem.
for the introduction. Let me know if anything goes wrong with my presentation. So I'm really excited to talk to you about our error suppression technique in continuous time quantum computing that we've been developing. And by continuous time, we mean an umbrella term which includes adiabatic quantum computing, quantum walks and quantum annealing. But before I get into the details of our error suppression technique, I need to talk to you about, not my slides aren't, oh, they are, okay, it's okay. Okay, about problem of expectation versus reality. Can you guys see the top of this, the slide?
There's an X, yeah, the mouse, it's white. It says expectation versus reality. Your mouse is in the middle at the top.
Okay, okay, cool. Right, yes, because I think I can just see like my mute button. So, okay, I'll just continue anyway.
And now you have a red pointer, good.
Yeah, okay. And so quite often when we're thinking theoretically, especially in continuous time quantum computing, we think of optimization problems. And we like to encode our optimization problems in these Ising models where we have, so this is a simple example of an Ising model. And we like to encode our problems such that the solution to our optimization problem is the ground state of an Ising model. And here's a simple example. So here we have 2 qubits. Each of these qubits have a field applied to them, H1 and H0. And these qubits are connected by a coupling strength J01. We can represent the energies of these Ising model by this Hamiltonian here. However, if we're thinking of more and more complicated optimization problems, we're going to need larger and larger Ising models to represent them. And also, we're going to need more and more precise values of fields and couplings that we want to set in order to find the right solution. However, this might be where reality may have to step in, because what we want to represent theoretically might not be the case that we can, because in a quantum computer we'll be limited by the resolution of the instruments that we're using. And in fact, we may find that if we're trying to represent a number like this, what we may actually be representing on the quantum computer is something like this. And the problem with that is, by doing the difference between these 2 values, you're shifting around the energy levels in your Hamiltonian. So much so that you may cause a flip between energies. And in fact, when you find the ground state to your optimization problem, you may be solving a completely different problem and therefore getting the wrong answer. So how do we stop finding the wrong answer? So a naive approach might be simply to just try it again, or have a secondary copy on which you can try and find the correct answer another time. However, we want to do better than this. So by repurposing and further developing an idea that was first developed in this paper here, we start off by connecting our 2 copies together. However, instead of connecting them ferromagnetically, we connect these copies together antiferromagnetically. So these 2 qubit spins want to oppose each other. And we also set the strength of these antiferromagnetic links to the minimum allowed by the resolution of our quantum computer. But despite connecting them together, we still treat these Ising models as quite separately, as in we check the ground states individually. And in order for us to consider our computation a success, we only need 1 or more of these copies to be correct. Why stop at 2 copies? We add a 3rd copy, and this introduces frustration into our system, further inhibiting error propagation between the copies. So how did we test how our technique worked? Well, first off, we replaced our simple 2 qubit models with more realistic NP-hard Sherrington-Kirkpatrick spin glasses, which were first studied in a continuous time setting by some of my collaborators in this paper here. So we generated 10,000 of these Ising spin chain glasses for sizes 5, 6, 7, and 9 qubits. And each of these 10,000 instances, the fields and the couplings were generated randomly within the interval -1 to +1. We then subjected each of these 10,000 instances to a lack of resolution which we defined as the number of allowed values, say the points on this dial that was allowed between -1 and +1. And this itself was defined by 2 to the p + 1, where p is the precision. And we varied this precision from 1 to 10. So as the precision increases, we're getting closer to the Ising model that we want to represent theoretically. And so next we wanted to check how well our technique worked. So we measured something which we called fraction correct. And that is the fraction of times when we had subjected our instance to a lack of resolution, that it still had the correct ground state. And first off, we did this on single copies to have something to compare it to. So these are disconnected copies. And then we repeated the process with our 3 antiferromagnetically connected copies in the same way and found the fraction correct in the same way. Remembering that we only needed 1 or more of these 3 copies be correct in order for us to consider the computation a success. We could also break down the measure of fraction correct of 3 copies into the fraction of times we had 3 copies correct, 2 copies correct, or 1 copy correct. And then we plotted this versus the precision to have a graph like this. So what you can see here is on the left-hand bars represent singular copies that are completely disconnected. And as the precision increases, we find that the fraction correct of these singular copies also increases. This is as expected because as we are increasing the precision, we're getting closer to the theoretical Ising model that we want to represent. On the right-hand bars, you see the results of fraction correct from the 3 antiferromagnetically connected copies. And what you can see here, interestingly, to us, is that there is an increase in fraction correct between the single copy and the 3 connected copies, indicating a benefit from using our technique. Also, interestingly, you can see that a lot of these bars are made up of instances where the system of 3 copies has either 2 or just one copy correct, indicating that the antiferromagnetic links and the frustration has a part to play in the success of our technique. Next, we wanted to analyze how well our technique was working on individual instances. So on which proportion of instances our technique was having a benefit, which proportion of instances our technique had no effect, and which proportion of instances our technique could be having a negative effect on. So to do this, we wanted to measure the results of the 3 copies given the result of the single copy. So for the one that had no effect, we measured when we measured the fraction where the single copy was correct and the 3 copies were also correct. To measure the fraction where our technique had a beneficial effect, we measured the fraction where the single copy was incorrect, but the 3 copies were correct. And finally, to measure any instances where our technique had a negative effect, we measured the fraction of times where our singular copy was correct, but our 3 copies were then incorrect. And we again plotted this versus precision. And these left-hand bars are still the previous singular copy bars that you saw on the previous slide. But next to them, the right-hand bars, we have split up differently. And what you can see here is that the improvement, as you might expect, is coming from those singular instances which are improved upon by using our 3 connected antiferromagnetic copies. However, you can also see on the top of the bars here that there is a sizable fraction that are actually being negatively affected by our technique. And this might look like a bad sign at first, but actually we realized that we could have, instead of just running these 3 connected copies together, we could run a external copy alongside it and therefore gain the benefits that we might have missed had we not had these 3 copies, just use these 3 copies on their own. And so by measuring from the left-hand bars to the right-hand bars, we can measure the overall improvement between a singular copy and from using our 3 connected copies with plus the external singular copy. And in order to see whether this worked just beyond 5 qubits, we then tested this on 6, 7, and 9 qubits and found that this improvement between a singular copy, which is the solid lines, to 3 connected copies plus an external copy continued for all the cases that we tested. And this shows a proof of principle that our technique works. So in conclusion, what we have found is that by connecting 3 copies via antiferromagnetic links of minimum strength, we have made our Ising models more robust to a lack of precision in the fields and couplings. This could potentially be used to increase the effective precision in computations. And finally, I would like to thank my collaborators on the project and my supervisors, Viv and Nick. And also thank you all for listening. Any questions?
Thank you. So where can we find more about this research of yours? Is there a paper?
Yeah, so very soon we're in the next week or so, we're gonna put our paper onto the archive. So that's the best place to look for more details.
Very good. If anybody has any questions, please go ahead.
Okay, I have a question. So you made the comment, and let me see if I can articulate this. I'm still thinking about what you're doing. You made the comment that when the test results slide, where you show 1 copy to 3 copies, 3 copies correct, 2 copies correct in green, and 1 copy in I think it's tan. You made the component, the statement that at 3 CP, you know, one showed the improvement over 1 copy. And when I looked at that comment, you mentioned that the tan box showed that improvement, but it didn't. The first line didn't show the 3 copies correct color, and I was wondering, you know, why would that? If you can go back 2 or 3 slides, I'll show you.
Okay, yeah.
It didn't show up until the third copy for P, I guess, underneath, and I think that just answers my own question.
Yes. So this is 3 copies correct. Yes. So this is when all 3 of the copies within the system have the correct ground state. Okay. Prior to that. So
prior to that, it wasn't.
There were 2 copies correct or 1 copy correct. So the green bars show that there were just 2 copies correct.
And so as time goes on, the time duration of this, that is becoming smaller and smaller and smaller, the differences between, and you measure the gap between that, and then you add an additional copy. Why would you add an additional copy? That's the next slide after this one.
Yeah. Mm-hmm. Yeah, so these bars are slightly different. So what we're showing here is, so the up to the blue and the green bars up to the top of those is showing the effect just from the 3 copies on their own. This third bar is actually showing when our 3 copies fail. So it's kind of like the potential improvement that we could get, but we're not actually there yet.
Okay, and then go to the next slide for me. Go back one. I'm sorry.
Oh, sorry.
Just right there. The differences between those 2 is actually the dotted line and the solid line are actually showing the improvement of the actual antiferromagnetic connections between the multiple Ising states. Is that what you're saying here?
Yeah, so it's showing an improvement. So this is the improvement between this just having a single copy and the 3 copies, but also the external copy as well.
So I didn't understand what that external copy concept was.
So it's just sort of like running a separate copy alongside that is completely disconnected at the same time, and also checking its ground state.
And the reason why you did that is why? I wasn't sure.
Is because some of the times when we're connecting the 3 copies, it's causing all 3 of them to become incorrect, when just running a single copy on its own would provide the correct answer.
Okay, got you. Now I see. It's just a checking mechanism.
Yeah.
You know? All right, and so I understand that. And so the next slide. Now, I wasn't following everything, so I'm just trying to get an understanding here.
It's okay.
And so this one here, can you just go over this quickly with me, real quick?
So
go ahead.
this is showing like the same as these lines that I've drawn on here on this
Right.
graph here, but for increasing sizes. So 6 qubits, 7 qubits, and 9 qubits, just to show that we're still getting the same improvement as we increase the size of our Ising bin glass.
Okay, and I get it. So now I understand. And so this is significant because as you increase this, are there going to be any more larger size models that you use here? Is that what your next
So
result?
currently we're actually limited by computational. So I'm just running this numerically, but it's kind of an open question as to whether there's kind of any analytical theory behind this that could explain why we're getting this improvement. So that's still an open question at the moment as to whether it continues.
I'm sure that's on your plate to try to figure that part out, because this is actually compelling. Thank you. That was my question. All right.
Thank you.
So before we transition to the next speaker, I wanted to mention the question from Jemma to the industry partners was, what would you like your company to achieve in quantum computing in the next 5 years? So basically, specifically to Charles, where is IBM going to be in 5 years, Charles?
Okay, so I was just pulling up all of the different places that we're looking at error correction and error mitigation. And I have a table that I wanted to show everybody on a list of the codes and pertinent property ranges that indicates the number of qubits for couplers. So we're looking at a lot of coupler work. And so I'm going to share this real quick. So I'm sure folks have seen this, that right now IBM is on our roadmap is published from a quantum computer perspective. And in order to reach fault tolerant in the next 5 to 10 years, it's all about connecting. For us, it's about, let me see if I can share this.
So is IBM going to be part of the quantum marketplace on the 5th of May or not?
No. But for us, it's all about couplers, right? Couplers between boards, couplers between subsystems, couplers between actual units themselves, right? So this is how you scale to fault tolerant quantum. And what that does is it opens up all kinds of different error regimes in quantum error correction and more importantly in error mitigation schemes. And so we're investigating different types of error correction. She's looking at basically annealing, Ising models that are associated with that. We're looking at surface codes, high genius surface codes, all these different surface codes that go across those couplers and across those quantum architectures. We use the honeycomb model. And so we're looking at multiple different error and quantum error correction and quantum error mitigation strategies. And so this is kind of a snapshot of most of them, and they deal with the different layouts of the specific area. I'm sure she's probably very familiar with all of these. And see, this is an example of, and I'm going to stop there. This is an example of what I said earlier, which is, what she's learning applies. She's looking at error correction across adiabatic systems. Those same concepts are the surface codes. She looked at Ising models, and she looked at antiferromatic. My English is not that good, Black American. Antiferromagnetic usage for coupling as it's a surface mode mode concept that she's actually doing. And so at the end of the day, these are all, she could drop right into our error correction team. You know what I'm saying? Yeah. I think she understood that table, quite frankly. Am I correct, Jemma? Yeah. So I'll pause there. Go ahead.
I put in the chat, I put a link. If people want to register, people who are currently here, if they want to register for the quantum marketplace on the 5th of May, D-Wave will be there, Quantinum, Cold Quanta, QERA, Xanadu, and a few other companies. They will show you what they can do right now. You could ask them, where are you going to be in 5 years? And they will tell you. They will not hold anything back.
Well, I can tell you, D-Wave is working on superconducting qubits. They're also trying to ring out the error and trying to encode optimization problems in a more effective and efficient way. I mean, we all are doing the same thing, right? So, Jim, I think that, just different approaches, but the same concepts. And, so opportunities abound for this,
Okay. Thank you, Jemma, for a wonderful presentation. We're going to move to the third presenter. We're running a little bit behind, Kayla Rodriguez.
Jemma, we'd like to hear from you when you get the theory figured out to why you have that improvement. All right.
Okay, so thank you once again, Jemma. We're moving to Kayla. Kayla, she is currently a postmaster's researcher at NIST. And while you're trying to share the screen, I'm going to say a few words about you. You got your bachelor's in physics at UCLA and master's in physics at the University of California, Riverside. You found your passion in atomic molecular physics, trapped ytterbium atoms with Professor Paul Hamilton. You work with Professor David Salzberg, and after UCLA at Riverside, further explored your atomic molecular physics interests. I think we were working with Professor Hammerling on molecular trapping experiment. From here, you transitioned again and switched to a new experiment in a Powell trap for quantum computing, which is the work that you're going to present today. So take it away. I think the sound.
Hear me now?
Yes, now I can hear you. Very good.
Okay, perfect. So today I'll be talking about electrons. I'm a researcher at NIST, but I will be presenting on my research from UC Riverside. And that basically aims to trap electrons in a microwave Paul trap for quantum computing applications. So basically, I'm going to go through this presentation in the order displayed. I started building this experiment from scratch, so I'll mostly be talking about the work I did to build up to it, while also making reference to the feasibility study paper on where we talk about trapped electrons as a possible alternative quantum computing platform. So first off, the motivation for this project, which is to adapt the advantages of ion trapping technology for trapping electrons in a Paul trap. And so two things on this. First is trapped ions have record coherence times greater than 10 minutes. And high fidelities. And for those of you who don't know, coherence is the ability to carry quantum information. It's stored usually in the phase. And the fidelity represents the percentage of error-free operations that can be done. So these are both really good things that we want to integrate. And so we want to integrate that for electrons. So for some background, basically, with an electron, it's trapped in a Paul trap, which is basically just a harmonic potential made from time-dependent fields. And basically, the way this is done with ions is you are able to trap it there with lasers and detect it out with lasers and things like this. But the way this works is the electron moves in this harmonic trap, and it creates image currents as it moves back and forth in the trap. And then attaching a resonant tank circuit can pick up the resonances. And then you can simply just detect the voltage drop across this tank circuit here. And this allows you to easily calculate things like the time constant, the induced current by the electrons, and that sort of thing. So the next thing I want to move into is the trapping. So one of the big goals with this project was to explore 3D printed traps. So basically in ion traps, you'll see some, maybe this sort of particular configuration. Can you guys see my mouse when I move it?
I can see it.
Okay, good.
Yes.
Great. Okay, so for an ion trap, you'll see this sort of big bulky thing where you have 4 rods and the ions are trapped here. And you can imagine that you're very limited by space. But although there are people who are trying to scale this down with fibers and things, and that's shown right next to it, where you have these chip-based ion traps where you move from this to this. And this chip-based ion trap is a lot more scalable. You can put it in a chip, but the problem is when it's a chip, it's 2-dimensional, and you lose a lot of that strong confinement that you get in these 3-dimensional conventional ion traps. So the big trap goal with this project was to actually combine both of these ideas to retain the strong confinement in the conventional ion traps, while also adding the scalability. And so this picture right here of the Eiffel Tower shows how flexible you can get with these 3D printers. This was at Lawrence Livermore. And the big idea of this is you can create these little spider-looking things that is basically just as scalable, but with these really big trap depths because of its 3-dimensional. So this is the big idea here. I wanted to show some prototype traps. This was one of the first thing I worked on at UCR. So basically these traps, for some scale, this wire is, 0.001 of an inch, and it connects to all of these electrodes. And so that's the prototype. And then the next thing was I was doing some failed wire bonding, but we learned a lot from this. Basically, 1, I learned how to wire bond, and 2, I reported to Lawrence Livermore the ease of wire bonding, essentially. And due to these results that aren't pretty, we were able to modify it in multiple iterations, and that is something that they're still working on. So there are two main trapping apparatuses that I want to talk about. The first one is the room temperature trapping. The second one is cryogenic trapping. The room temperature trapping is something that I was building and working on. I started with just an empty optical table. The cryogenic trapping is something more along the lines of that we were simulating. And this is more talked about in my recent paper that I can give at the end of this. Okay, so the room temperature trapping. So the actual room temperature trapping builds off this work done with UC Berkeley, who we collaborated with. And basically they showed that you can, in fact, trap an individual electron in a Paul trap. And I basically took that idea and I built, our own sort of chamber so that we could be able to do that. And then looking even further inside the chamber, you have these different things. So these wires connect to the detector, which the electron gets shot out of the trap and detected by this multi-channel plate detector. And then the others are the DC and RF electrodes to actually make the RF trap. And then here's some nice pictures of how this actually turned out. So for scale, this is like maybe 3 feet was the biggest vacuum tube I had. So this is pretty small, and the only lasers that we use are for photoionization. And so what's very nice about using electrons rather than ions is that you have this essentially almost laserless system where this is the scalability. And this is for one, but this is mostly just for testing different trapping architectures. Okay. So now an important thing to note that at room temperature, you cannot use the electron spin to actually perform quantum gates. You need to use a cryogenic system. So this is primarily what I worked on in the feasibility paper that I was on. And the reason why is because you have these spin-dependent forces are very, very small, and thermal forces usually outweigh those very much so. So to actually utilize this sort of quantum computer, you would need to completely go cryogenic. So the idea here, and this is a different sort of trap than what I was speaking about earlier. This is a 2-layer design rather than a 3-layer design. Again, building off of what the collaboration was doing. But the idea is that you have this bottom layer, which generates this magnetic field, and it generates, so you have your magnetic field gradient, and it also generates the electric fields. These are your RF electrodes here, your DC, and then these hairpins are your 1 amp current to generate a magnetic field to actually do the quantum operations on the electrons. And then this top one here picks up the image currents made by the electron's motion. So this here is sort of the way this works. You have this whole system be cryogenic, and that would allow this to be the this would allow it to be a quantum information computer. Okay, so moving on. So to actually go cryogenic, you have very limited cooling power. So to do this, you have to be very careful about what you pick. And so the actual thing that I was looking at in particular was this thing is going to be in 4 Kelvin, but the idea is, can we do even better and put this in, have 1 layer, let's say the top one for the pickup electrodes be at 0.4 Kelvin and the other one be at 4 Kelvin, and use 2 cooling stages. So what I did from here is I analyzed different sources of heat load on the system. There's, radiation conduction from 4K to 0.4K. But we found that actually the Joule heating was the biggest issue in terms of the heat load. And we were able to mitigate, conduction by putting proper heat sinks on things. But for this, we just made sure to, so on the left here, we have a simulation, and I want to note that I put it in DC only as to sort of give a visual of how hot this gets. This was just a preliminary simulation, but the actual stuff in the paper, it's all just done by calculation. So this is just this exact geometry. And so the bottom being, or the bottom being 4 Kelvin and the top being 40 millikelvin, because that's what we were initially simulating. And by taking in the parameters, you conclude that the resonance circuit on top, so this one, has a heat load of about 150 microwatts, which is well within the range of a commercial dilution refrigerator of 1.4 milliwatts. So that's the biggest thing here. And I want to note before leaving this topic is that, if there's room temperature trapping and cryogenic trapping, why not just go cryogenic if that's the full goal in the first place for a quantum computer? And the idea is these cryogenic systems, they're a lot harder. You have to, be careful with material choice and things like that. And we had more of the room temperature stuff available to us. But the room temperature stuff, it allows us to quickly change out and explore different trapping architectures. And when we know that the room temperature trap can trap electrons through this destructive detection, then we just, the idea, pop it into the cryogenic one, and we know that this trap works, and you put it in the cryogenic one, and now you have a trap that works for quantum computing, hopefully. So to conclude, basically, using trapped electrons to explore possibly new quantum computing platform through the use of trapped electrons. So this is just adding to, the plethora of things. I mean, you have superconducting qubits and ions, and by taking things from each thing, then hopefully we can all build up a new sort of thing or just contribute to the field. But basically, to summarize, we utilize the advantages of ion trapping to trap electrons, aka trapping the Paul trap. And one thing to note is that with cryogenic trapping, you do not have to do destructive detection of the electrons. You detect them through resonance circuit. And for ions, you use a laser. And I also explained the details of 3D printed traps as a long-term goal, as well as exploring the different architectures that can be placed with the room temperature apparatus that I had. And I also briefly showed the cryogenic environment, which is necessary to actually utilize electrons as actual quantum objects for qubits for quantum information processing. So with that, I want to put some references here and thank my team and also the whole UC-wide collaboration for this project. And that's it.
Thank you so much. Wonderful presentation. And if anybody has any questions, go ahead.
Kayla, can I ask a quick one?
Yeah.
So I know that one of the big issues with ion trapping for quantum computation is that you have pretty low gate speeds. Does using electrons help that at all due to the fact that they're so much lighter?
Yeah, actually, that's a fantastic question. That's one of the major things that we do talk about in this paper here, is that it increases it by several. I don't want to. I haven't done this in a couple months, but goes to 300 megahertz for these axial frequencies, and frequencies are a lot faster for everything. So drive frequency, gigahertz, transverse gigahertz, but axial frequency is 300 megahertz, and so that sort of thing with the charge to mass ratio being so small that you actually do increase gate speeds.
Sweet, thanks.
Mm-hmm.
Any other questions? So if there are no other questions, first of all, apologies for going so slowly. We have a fourth presenter. Joshua Leaney is an undergraduate student at Loyola University in New Orleans. He majors in physics and computer science. Josh spends his time either in a classroom or on a basketball court, as he's a student athlete in the men's basketball team who just won the national tournament for the National Association of Intercollegiate Athletics. His primary field of focus has been on electromagnetism under the mentorship of Dr. Jamileh Beg Mohammadi. His research has been focused on combining his passions for programming and physics together to create simulations assisting educational opportunities. Go right ahead, Josh.
Thank you very much for having me. It's a pleasure to be amongst you all to present what I've been working on for the last 8 months. I've already been introduced, thank you very much, but I'm Josh Leaney. My professor that I work underneath is Dr. Jamileh Beg Mohammadi, and as mentioned earlier, I'm a computer science major and physics major undergraduate. So this is a very rudimentary example of where things can lead to, but I'd like to discuss the results of what I've been doing over the last 8 months, in particular, how this can be useful for future education purposes. So what is the purpose of this research? The purpose of this research is to integrate virtual reality into education. And one of the reasons that we try to achieve that is that in physics, particularly at undergraduate level and high school level, it's very hard to accommodate different people's learning styles when some people aren't as motivated to engage in the material. So one way you can do that is by, accommodating to the physical nature of someone's being, the audible nature of someone's learning as well, and then also the visual. And virtual reality is something that can achieve this quite easily as long as the integration and immersiveness of VR is used for the correct purposes. There's a very difficult role that educators have in teaching physics in 2D, because as displayed on screen, you have, your cubic structures, substructures and of the type, and they're very hard for people to understand the symmetry of, and to understand basis vectors and how all of these interactions can integrate into electromagnetic properties and electrical properties as such. So the result of my research so far, it was originally intended to be built for a specific class at Loyola. And this specific class is teaching solid state physics. And what I've achieved with this is using the Unity platform, being able to create a 3D game-like feeling towards learning. And this is quite an interesting approach for me, because I've always been someone who's super into the tech side of things, who's super into understanding how the inner workings of things work, and being able to visualize that and interact with these objects and understanding it is much easier for me than reading from a textbook that is talking about basis vectors and symmetry on a 2D scale when they're not even particularly mentioning the complexities of different substructures. So what ended up happening, and what I've got displayed on screen, is this is a recording of me walking in my 3D environment that I have developed. So the particular focus here of this main area is visualizing everyday objects and observing them in 3D and seeing how the substructures can be visualized and understanding the symmetry of them, so that when people apply that logic to an exam or to things of that nature, you can see how different objects will integrate together. And on screen, I'm showing the simple cubic and the face-centered cubic ladder structures in 2x2 unit cells. Then the whole idea of being able to familiarize yourself with all these different structures is quite a unique thing, because sometimes for some people, you struggle at least with connecting real life to the theoretical. And I find that it helped me to understanding how these different things work. And of course, I'm just showing you that you can select all these different types, but when you select like mesh versus full, you can see how different substructures integrate and look for different real life objects. So for some of them, you will see face-centered cubic. For some of them, you see body-centered cubic. For others, you'll see modified body-centered cubics, and you've got the simple cubic obviously there too. The next, and I think the most important thing that I was able to develop in my 8 months of scripting and developing in this environment, was being able to accommodate 4 basic substructures and then integrating them with different dimension levels and scaling. Because sometimes you want to bring the quantum, the microscopic nature of things into the macroscopic world. And when you're in this, you don't feel like you're in a real world, you're in a whole new world. So that's one thing that makes this VR so interesting, because I can now look at different structures in 1x1, 2x2, 3x3, and extend that continuously. And this is only a very simple edit of this, because I've yet to continue the research, but you can extend this to infinite dimensions if so choose to be. The next part of it is actually like building it, and that's why it was intended for this one particular class in solid state physics. And when you can build something and you can accommodate to someone's physical nature of grabbing something and putting it in, with VR, you have the haptic feedback of a remote control, right? It shakes when you're grabbing something, it shakes when you're doing stuff. Well, when you can build these and you can have a professor educate you on how that interaction works, or for example, building sodium chloride as a on a microscopic level, suddenly you're able to appreciate what's going on more than just, oh, this is a cube with spheres in the corners. And there's 3 basic colors as well that I've used to pick different atoms and integrate this in different ways. One of the important features as well of VR is integrating physicality and being able to like manipulate these by hand movements and gestures. And one of the particular useful ones that I have integrated is being able to rotate structures to observe different symmetries. This is quite useful when discussing symmetry planes, as well as basis vectors for different types of structures, because although these are very simple, as soon as you start expanding into different other substructures, it becomes much harder to understand what a 0.125 in this direction looks like, and those types of things when integrating these all together. On screen, I'm continuously showing you guys how you can manipulate these structures. And one of the things that is very useful is when you're looking at these 3x3 structures, you can scale them up and then move them around, and you can have all these things together where you can stand back and you can grab and you stand back, and suddenly you're not looking at it so closely, but you can appreciate it for its full nature as well. And then obviously with switching and different things like that. There are many future developments that need to come through this project, some of them being the magnetic field interactions and parallel and anti-parallel magnetic field arrows that will be displayed within the game-like feeling, where you could see like spin of atoms, and you could see how bringing a magnet towards a structure will morph the substructure to focus on that one side, and it will like change the way that it interacts with other objects. There's also integrating electrical properties and then increasing the portability across multiple devices. When I first started this, I started in OpenGL, and OpenGL is a language and used on computer graphics. And what it does in particular is you're able to run it on multiple different computers, no matter what device you have, you can run it across every single platform. Well, it's great that you can do that and you can manipulate all these things, but you don't have the 3D physical feeling of this. You can see it, but you can't handle it. You can't feel it. You can't appreciate it for its complexity, in my opinion, at least. I'd like to say thank you for listening to my speech. This research was funded by the Father Carter Fund at Loyola University, and I appreciate you guys all for listening. And if you have any questions for me, I'd love to answer them.
So once again, thank you very much for your presentation. I think this is very creative, and Ellen Windsor has a project that is related to this, but I'll just say this: quantum is the world of the very small, and everybody, there's been a lot of debate. Should we keep telling people that nobody understands quantum, in the sense of Richard Feynman, who was actually telling people that you can't say that you understand it, but how could you understand it if you didn't grow up in that environment? But with a virtual reality of the kind system tool that you're developing, people could start, I suppose, experiencing those phenomena in this environment or an environment like the one that you created, so that people could start acquiring intuition beyond the mathematics that we normally use to calculate. So
yeah, I totally agree with that statement, that if you could extend this to someone in high school who's just being introduced to it, suddenly you'll have so many more people interested in the topic and so many people who will pursue this at a higher level than they would otherwise. And that's my opinion.
Mm-hmm.
Yes.
I have a question. So you showed cubics. Now, I took Kittle. Kittle is I have the old book, the old version, solid state physics. I mean, if I remember correctly, it was 14 different lattice structures.
Yes, correct.
Right. You only show one, right? The cubic.
Mm-hmm.
Does it?
The reason I did this is to keep it simple, because this is something that I've only been developing over the last 18 months. Mm-hmm. So I'll pause it on a video.
Right. So you still have a ways to go to implement the complete solid state class, correct?
Yes, correctly.
Okay.
Uh,
You know, so but this is, you know, it is very, very impressive. And I think, as Adrian was mentioning, anything visual will get younger people engaged in a more meaningful way. You know, I'm talking about K through 12. And so, yeah, I'm very impressed. What about augmented reality, right? Or, you know, are you looking at, you know, that to add to this virtual reality environment?
Yes, I am. That's something that's a further extension of what I'm doing currently. I have worked in a couple of internships and stuff that implement augmented reality and virtual reality both separately and combined. This is something that I would love to continue. But as a senior student who was going through a national championship run with basketball, I didn't have a lot of time, as you might expect, with all the trainings and workouts and other things that were going on at the time.
If the rest people on the basketball team were just like you, they could work for you, and then you would make a lot of progress. So tell them that it's time for them to help you.
I wish they had the intellect to be able to code like I can code, but unfortunately, everyone's got their own pursuits in college.
Right.
Yeah, I'd like to connect you with Ellen Windsor.
Right.
And I wish she was on the call today, but we may have some opportunity for you to be associated with QED-C in some fashion. So we'll wait to have that conversation. Adrian Windsor.
I have seen 3D representations of but you don't interact with them, you just watch them, but they're still impressive. Jim Freerichs at Georgetown has quantum mechanics for everyone. And at the beginning, he has some 3D simulations of Stern-Gerlach.
Right.
And the thing is that even a precession motion, it's just hard to understand it. But if you see it, or you can sort of approach it, relate to it, it just becomes more concrete.
And it becomes a situation where Joshua is developing an application. I mean, at the end of the day, he could probably use to be around folks that are doing something similar, run off each other's ideas or whatever.
Yeah.
But, you know, at the end of the day, we're going to connect you with Ellen. We're looking to do something in the fall, a crowdsourcing type application for this effort at the Wilson Center for young students to be able to do some of this activity in creating the metaverse themselves. And so at the end of the day, you know, Joshua, if that's something that you're interested in getting involved with, we'll connect you to the right folks.
Yeah, definitely. That would be something I'd very much appreciate.
Good. So we're going to follow up on all this with you.
I just want to jump in. Can I interrupt? First of all, Josh, this is great. Just for context, I was working in the virtual universe community at IBM 10 years ago, doing things like resing out rhodopsin molecules and bringing pharma execs in world and showing them how they were constructed. So a huge fan of this kind of work. You mentioned OpenGL. Is this only viewable like with a headset, or are you looking at like Unity 3D or OpenSim or other ways to make this browser based?
Yeah, this is definitely something that is wanting to be implemented on that level. I would love to work and push it towards like the build, like, you know how you can turn your phone into a VR headset? I forget what it's called. I think it's called Google Glass or something
Cardboard,
like that.
Google Cardboard.
That's it.
Yeah.
So something like that would be awesome if people could be able to do what I'm doing with a $500 headset on their phone. That's why this is something that I would love to continue to pursue. It's just something I haven't had time to completely expand upon in my time here.
Now, Google has a whole portfolio, right, of 400 expeditions that are VR experiences viewable through the cardboard. They're sort of $20, VR viewer. This would be perfect for that kind of thing. Again, to get kids interested in it,
Yeah, that's why I have a lot of passion towards this kind of thing. I love being able to provide resources for people. And that's one of the things that drove me to do this research while I was at Loyola.
Great, thank you.
I had a question for Josh. So Josh, you got multiple things going on here. You're actually researching education as much as you are researching new ways to teach quantum. Does your vision include like a classroom where multiple people are involved with the activity, or do you picture this remaining a solo endeavor?
I can see this as something that definitely goes towards being a multi-user experience. For example, loading into this particular game and having like a professor wear it and being able to do this remotely through servers. That's something that could totally be a non-solo experience where you could have educators and different people interacting all together on this different type of stuff.
My daughter's a middle school science teacher, and the Workforce Development National Strategic Plan, was published a memorandum a month or so ago. And they're just talking about the need for this education to begin earlier and earlier if we're to have an effective, quantum workforce in the future. And this is just an inspiring idea, as far as what a great way to introduce young students to, quantum information science in a fun and engaging way, especially if they could, collaborate on problems. So well done.
It's what we've been looking for, Joshua. And so I appreciate you, Adrian, and bringing Joshua to our attention. And we will be following up with you. There may be some specific QED-C projects that you may be able to work with us on. And I'm gonna set up a call between Adrian, you, myself, and Ellen, probably sometime next week, if you have time. We'll work towards your schedule.
Yeah, of course. No, I'm much more free now that all the national championship stuff is over and I don't have to worry about my teammates and my coach anymore as a senior. So it's very nice.
Awesome.
And with this, we're approaching 90 minutes. Any other questions before we close this?
I just want to say thanks to all the students for participating. I mean, terrific to take time out of your day and to put together a presentation that captures your great work, and for taking the time to share with us. So thank you to all four of you.
Kayla had to go, but we thank you,
I want to make
Kayla.
one statement as well. What I've seen here is creativity on every level, right? Creativity from an experimentalist perspective, creativity from, in Joshua's case, just in a new channel for learning, creativity, and how to annihilate aspects of the Bose-Einstein condensate, the boomerang effect. There's been just a plethora of talent here. And, even though there may be a small audience here, what we will commit to you if you join this office hours is we will make sure that every one of you get connected with someone in the field in your interest that is along the lines of what you're doing research in. It's not just Joshua. And so what we will commit to you guys to do is, if you join that, we will connect you with a mentor and make sure that your research area, that you got the right person from the right company. We got folks from each of those companies on our membership list, and we'll do our part to make sure that this time is impactful for you. I know it's been impactful for us. Thank you.
So this was recorded and our members are going to watch it. I want to thank Kayla and Jemma and Roshan and Joshua for coming here today. And I want to point out that our next meeting is going to be on June 14. Thank you all, and we'll see you later. Thank you.
Thanks,
again.
Adrian, for organizing.
Okay,
Awesome.
bye-bye.
As usual, Adrian. Awesome.
Okay, no problem.
See you, man.
Bye-bye.